Right now, as you're listening to this, there is something in your bloodstream, in the exhaust pipe of your car, and possibly on the finger of your left hand. Something that, according to every law of physics and every rule of planetary geology, should not be accessible to you. It should not even exist anywhere near the surface of this world. It is older than your planet by 4 billion years. It watched the moon being torn from the young Earth in a cataclysm of unimaginable heat. It survived the asteroid that ended the dinosaurs, barely flinching. And when your great-great-grandchildren are dust, when the cities you know are buried under 10 feet of soil and silence, this metal will still be lying in the ground, unchanged, untouched, utterly indifferent to the passage of time. Its name is platinum, and it is the most misunderstood substance in human history. Not because it is rare, though it absolutely is. Not because it is valuable, though it is worth more per ounce than almost anything you can name. But because for the first century that Europeans held it in their hands, they genuinely, stubbornly, expensively believed it was worthless garbage. And the story of how that mistake happened, and what it cost, is the story of how human beings have always treated things they do not yet understand. We start in Colombia. Not the Colombia of modern cities and coffee plantations, but the Colombia of 1540-something, of Spanish soldiers in iron helmets slogging through jungle humidity so thick you could drink it. The air smelled of rot and river mud and the particular kind of desperation that comes from being 10,000 miles from home, losing men to fever every week, and answering to a king who expected miracles. The Spanish crown had sent these men for one reason and one reason only: gold. Not silver, not land, not spices. Gold. Gold was God and salvation and power, and the entire point of crossing an ocean that most educated men of that era still half believed might drop off into nothing at the edges. These were the conquistadors, the conquerors, and they had heard the stories of cities built from gold, of rivers where the sun reflected off the riverbed in pure, brilliant yellow. And so they worked the rivers, dragging wooden panning dishes through the cold, rushing water of the Colombian highlands, watching carefully for that unmistakable gleam. Sometimes they found it, and sometimes, mixed in with their gold, heavy, gray, stubborn little nuggets, they found something else. Something that did not gleam. Something that sat in the pan like a sullen intruder at a party it had not been invited to. When they tried to work it the way they worked silver, hammering it, melting it over open fire, the metal just sat there, red hot, glowing like an ember, but refusing to liquefy. It would not flow. It would not pour. It absorbed heat like a stone absorbs sunlight, and when the fire died, it simply cooled back to the same gray lump, unmoved, unmarked, annoyingly unimpressed. The soldiers named it platina, a diminutive of plata, the Spanish word for silver. Little silver, cheap silver, fake silver. The contempt in that name was deliberate. These men were not metallurgists. They were warriors and opportunists and survivors, and their instinct told them that anything which refused to behave, refused to melt, refused to be beautiful, refused to be gold, was beneath their concern. So they did what people have always done with things they do not understand. They got rid of it. They threw it back into the rivers, fistfuls of it, tossed over the side of their boats, sinking through green water to the rocky riverbed below. And here is the thing that should stop you cold, the thing that should make you put down whatever you are holding and just sit with the weight of it for a moment. Those gray nuggets that the conquistadors threw away without a second thought? In today's market, a single ounce of platinum is worth well over $900. The deposits they were standing on, the rivers they were panning, the material they were literally discarding into the water, that was a fortune so vast it exceeds the entire value of all the gold the Spanish Empire ever managed to ship back to Madrid. They crossed an ocean, endured 3 years of misery, and threw away more wealth than they ever found, because they did not have the framework to recognize what they were holding. That image of a soldier, sunburned and impatient, flicking a gray stone off the tip of his finger into a river, is the image I want you to carry through this entire story, because it will repeat. History has a way of doing that with platinum. Every century or so, someone encounters this metal and misses the point entirely, and every time they do, the cost is staggering. To understand why those Spanish soldiers were handling something so extraordinary and so completely failed to recognize it, we have to leave the Colombian jungle behind entirely. We have to leave the Earth. In fact, we have to leave the solar system. We have to go back, way, way back, to a time before the sun existed, before planets had formed, before there was anything in this corner of the galaxy except a slow-spinning cloud of gas and ancient dust. Because platinum did not form here. It did not form anywhere near here. And the story of where it came from is, without any exaggeration whatsoever, the most violent, the most extreme, the most cinematic origin story in the entire periodic table. To tell it properly, we need to talk about how stars work. A star is, at its core, a nuclear furnace. For billions of years, it fuses lighter elements into heavier ones, releasing energy in the process. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen, neon, silicon. Each step releases heat and light. Each step keeps the star burning. This is the engine of every sun you have ever seen, including our own. But here's the thing that most people do not know about that process, and it is a thing that changes everything. The nuclear fusion process in a star's core hits a wall, a hard, physical, inescapable wall. And that wall is iron, element 26. Once a stellar core starts producing iron, the party is over. Because fusing iron does not release energy, it absorbs it. For the first time in the star's multi-billion-year life, the nuclear reactions are consuming more than they produce. The internal pressure drops. Gravity, which has been held at bay this entire time by the outward pressure of nuclear fire, suddenly wins. The star collapses inward in a fraction of a second, and then explodes outward in what we call a supernova, one of the most energetic events in the known universe. Now here's the question that should keep you up at night if you think about it long enough. If stars can only naturally produce elements up to iron, element 26, then where did all the heavier elements come from? Where did copper come from? Where did gold come from? Where did platinum, element 78, more than 50 steps beyond iron's wall, come from? The answer is one of the most dramatic discoveries in modern astrophysics, and it was only fully confirmed in 2017, just a few years ago. The answer is neutron stars. A neutron star is what you get when a massive star collapses and the core survives as an impossibly dense remnant. We're talking about an object roughly 12 miles across that contains more mass than our entire sun. A single teaspoon of neutron star material would weigh approximately 4 billion tons on Earth. They are not just stars. They are the most extreme objects in the universe that have not yet become black holes. And sometimes, not often, but sometimes, two of these objects find each other in the darkness of space. They begin to orbit one another, locked in a gravitational dance that can last for hundreds of millions of years. As they orbit, they radiate gravitational waves, ripples in the fabric of space-time itself, predicted by Einstein, but only recently detected by human instruments. Those gravitational waves carry away energy, and as energy bleeds away, the two neutron stars spiral closer and closer, moving faster and faster, until the moment comes. The moment when they finally collide. That collision, called a kilonova, is not an explosion in the ordinary sense of the word. It is something closer to a factory. In the unimaginable temperature and pressure of two neutron stars merging, atomic nuclei are bombarded with neutrons so rapidly that the ordinary rules of nuclear physics break down. Atoms capture neutron after neutron faster than they can decay. This process, called the R process, from the word rapid, builds heavy elements the way a mason builds a wall, stacking one neutron onto another in milliseconds, climbing the periodic table past iron, past zinc, past mercury, all the way up to and beyond platinum. In the moments after a kilonova, the debris cloud expanding outward at a significant fraction of the speed of light is rich, extraordinarily rich, in gold and platinum and all the heavy elements that no ordinary stellar process can produce. We know this is true because on August 17, 2017, the gravitational wave detectors LIGO and Virgo picked up a signal. A faint ripple in spacetime, the unmistakable signature of two neutron stars spiraling together and colliding roughly 130 million light-years away. Telescopes around the world swung to look at the source. They found a brilliant blue flash fading to red, exactly what the physics of a kilonova predicts. And in the spectroscopy of that light, astronomers found the fingerprints of heavy elements being forged in real time. They estimated that this single event produced somewhere between 3 and 13 Earth masses of gold and platinum combined. One collision, one brief flash across 130 million light-years of void. Enough platinum to outfit every human being who has ever lived, with immeasurable amounts left over. That is the lineage of the metal in your wedding ring. That is the ancestry of the gray nuggets the conquistadors threw into a Colombian river. Born in the death scream of colliding stellar corpses, scattered across space, swept up into the dust cloud that became our solar system 4.5 billion years ago. When you hold platinum in your hand, you are not holding a piece of Earth. You are holding a piece of something far, far older than Earth. You are holding the shrapnel of a catastrophe that happened before this planet existed. So now we have platinum. It exists. It was forged in the furnace of colliding neutron stars, scattered across the early solar system, swept up into the material that condensed to form the young Earth 4.5 billion years ago. Problem solved, right? Except not really. Because here is where the story gets its first genuinely disturbing twist, the kind of twist that makes you question whether any of this should have worked out the way it did. By all rights, by every principle of planetary physics that we currently understand, platinum should be completely inaccessible to us. Not rare, not difficult to find. Completely inaccessible, as in locked away on the other side of 3,000 kilometers of solid rock, forever beyond our reach. Let me explain. When the early Earth was young, and I mean very young, in the first 100 million years or so of its existence, the entire planet was molten. Not just warm, not just volcanic, completely, globally, ocean to mountain range molten, a ball of liquid rock and metal spinning through space, slowly cooling over millions of years. During this period of molten chaos, something called differentiation occurred. It is a remarkably simple process. Heavy things sank, light things floated. Iron and nickel, which are relatively dense, sank toward the center of the planet and formed what would become Earth's iron core. Silicate rocks, which are relatively light, floated to the surface and formed what would become the mantle and the crust, the part we live on. Now, platinum is denser than iron, significantly denser. Iron has a density of about 7.9 grams per cubic centimeter. Platinum's density is 21.4 grams per cubic centimeter, nearly 3 times heavier. When the young Earth was entirely liquid, platinum did not float. It did not stay near the surface. It followed the iron downward, all the way to the core, sinking through the liquid mantle like a stone through water. The geochemical calculations are sobering. The Earth's iron core contains, by some estimates, roughly 90% of all the platinum group metals that came with the original material that built our planet. 90%. Locked away at the center of the world, at a depth where the pressure is 3.5 million times higher than what we experience on the surface, and the temperature exceeds 5,000 degrees Celsius. It is gone. Permanently, irrevocably, forever gone, at least as far as human civilization is concerned. The platinum that we mine, the platinum in your catalytic converter, the platinum that treats cancer patients, none of it came from Earth's original endowment. It came from somewhere else, and it arrived much later. The story of how it arrived is called the Late Heavy Bombardment, and it is one of the most violent episodes in the 4.5 billion year history of our world. Here is what the evidence tells us. Between roughly 4.1 and 3.8 billion years ago, which means several hundred million years after the Earth had already formed and cooled and developed a solid crust, the inner solar system went through a period of extraordinary violence. For reasons that planetary scientists are still debating, the orbits of the giant outer planets, Jupiter, Saturn, Uranus, Neptune, shifted. And that orbital reshuffling sent an enormous swarm of asteroids and comets flooding inward toward the rocky inner planets. The Moon still carries the scars of this period, the great craters you can see on the lunar surface on a clear night, Mare Imbrium, Mare Orientale, the great basins that pock the moon's face. Most of them formed during this bombardment. The Earth was hit too, and hit hard. Thousands upon thousands of asteroids, many of them large, slamming into the young, solid crust of our world over a period of hundreds of millions of years. And those asteroids, those chunks of primordial rock and metal that had never gone through the differentiation process, never been part of a large molten planet, were full of platinum group metals. The platinum and gold and iridium in those asteroids had never had a chance to sink away. It was still distributed throughout, mixed evenly into the rocky matrix, and when those asteroids hit the Earth and melted into the crust during the late heavy bombardment, they left their metals behind. The platinum that we mine today, in South Africa, in Russia, in Zimbabwe, is almost entirely derived from this late-arriving cosmic payload. It is asteroid material, left over from an ancient catastrophe, distributed through the upper layers of the Earth's crust by billions of years of geological churning. Think about what that means for a moment. When a geologist in South Africa descends into a platinum mine, they are not digging up a piece of Earth. They are, in a very real and literal sense, digging up meteorite debris. When you wear a platinum ring, you are wearing asteroid shrapnel on your finger. The gold in the ring next to it? Same story. The iridium that they use to make the tips of high-quality spark plugs? Also asteroid debris. We did not find these metals by mining the Earth. We found them by recovering the remnants of ancient cosmic impacts, preserved in the rock for billions of years. Everything that makes our technological civilization possible, the metals that conduct electricity, resist corrosion, catalyze chemical reactions, a surprising amount of it arrived from outer space, delivered by a bombardment so intense it would have sterilized any life that existed at the time. And here is the most disorienting part of this realization. If that bombardment had happened slightly differently, if the asteroids had been slightly less metal-rich, or if they had arrived at a slightly different angle, or if the geological processes that concentrated their metals into mineable deposits had not played out the way they did, platinum might exist on Earth only in quantities too small to ever find, let alone use. The thin veneer of asteroid-derived platinum smeared across the upper layers of Earth's crust, concentrated by billions of years of geological accident into the narrow reefs and layers we can actually mine. That is not the default state of the universe. That is an extraordinary piece of luck. We did not inherit this metal, we stumbled onto it, in the dark, by accident, and then threw it in a river because we did not recognize what it was. Platinum arrived in Europe in the early 1700s, tucked into shipments from the Spanish colonies, sometimes as samples sent by curious naturalists, sometimes smuggled in the pockets of sailors who thought the strange gray metal might have some undiscovered value. The Spanish crown, for its part, was mostly suspicious of it. For decades, the official policy was to dump confiscated platinum back into the sea, partly because they could not figure out what to do with it, and partly because its density made it dangerously useful for counterfeiting gold coins. If you knew what you were doing, you could create a platinum core inside a gold shell, and the coin would feel exactly right in the hand, weigh exactly right on the scale, and pass every test a mint inspector of that era could think to apply. The Spanish crown solved this problem the way governments have always solved inconvenient problems. They outlawed the metal and tried to make it disappear. It did not disappear. It arrived in London and Paris in the hands of scientists who recognized immediately that this was something unlike anything they had encountered before. And those scientists proceeded to spend roughly a century making very little progress, because platinum, it turned out, had absolutely no interest in cooperating with 18th century technology. The central problem was the melting point. Every metal that European craftsmen and scientists knew how to work, gold, silver, copper, iron, lead, tin, had a melting point that was achievable with the furnaces and kilns of the era. The hottest furnaces available in the 1700s could reach perhaps 1200 degrees Celsius on a very good day. That was enough to melt iron. That was enough to smelt almost anything the old world's metallurgy required. Platinum melts at 1768 degrees Celsius. The gap between what those furnaces could achieve and what platinum required was not small. It was not something you could bridge by building a bigger fire or using better bellows. It was a fundamental technological barrier, the kind that requires a completely new approach rather than just more of the same effort. So the scientists tried everything else. They tried dissolving it in acids, the standard way of isolating and purifying metals in the chemical tradition of the time. Platinum laughed at them. Hydrochloric acid, the acid strong enough to dissolve most metals with alarming ease, did nothing. Sulfuric acid? Nothing. Nitric acid, the acid so reactive it was nicknamed the destroyer of metals, the acid that dissolves silver and copper like sugar in warm water. Nothing. Platinum sat in its beaker of nitric acid and did not even change color. The only thing that dissolved platinum at all was aqua regia, a smoking, fuming mixture of 3 parts hydrochloric acid to 1 part nitric acid, one of the most aggressively corrosive substances that a chemist of that era could produce. And even aqua regia worked slowly, reluctantly, as though the platinum were doing it a favor. The scientists of the 18th century were not accustomed to things they could not manipulate. These were men who had dissolved mountains, who had taken apart the composition of air and water, who had mapped the chemistry of gunpowder and dyes and medicines with confident, systematic precision. The idea that a metal could simply sit on their bench and refuse, just categorically, stubbornly refuse, to behave was profoundly unsettling. Antoine Lavoisier encountered platinum and found himself stalled. This is worth pausing on, because Lavoisier was not a man who stalled easily. He is one of the giants of chemical history, the man who named oxygen and hydrogen, who demolished the ancient phlogiston theory of combustion, who wrote the first modern chemistry textbook and essentially gave the science of chemistry its conceptual foundations. He performed the definitive experiments that proved that matter is conserved, that you cannot create or destroy it, only rearrange it. He was, by any measure, the most formidable chemical mind of the 18th century, and platinum beat him. Not permanently. Lavoisier understood its composition well enough, identified it correctly as a distinct element, but he could not work it, could not shape it, could not use it the way a craftsman or engineer would need to use it. It remained a curiosity, a sample in a glass case, scientifically interesting but practically useless. Then came William Hyde Wollaston, and the story of platinum takes a turn that belongs less in a chemistry textbook and more in a spy novel. Wollaston was an English scientist, physician, astronomer, chemist, a man of formidable intelligence and, crucially, formidable patience. In 1802, he acquired a quantity of crude platinum ore and began working on it in his private laboratory, quietly, methodically, telling almost no one what he was doing. What he eventually developed was a process for purifying platinum and working it into useful forms without ever actually melting it, a technique we would now recognize as a precursor to powder metallurgy. He compressed platinum powder under enormous pressure into dense, workable forms. He could make crucibles. He could make wire. He could make laboratory equipment of a quality and chemical resistance that nothing else could match. It was a genuine breakthrough, the kind of discovery that would normally be published immediately, shared with the Royal Society, announced to the scientific world. Wollaston did not publish it, not for 20 years. He kept his process completely secret, told his laboratory assistants that what they were doing was confidential, and quietly built a very profitable side business selling platinum laboratory equipment to chemists across Europe, without ever revealing how it was made. For 2 decades, he was the only man in the world who could reliably produce pure, workable platinum. And the reason he kept the secret? It was not simply greed, though the money was certainly welcome. It was something more alarming than that. Wollaston had done the math. Platinum's density, 21.4 grams per cubic centimeter, sits between gold at 19.3 and nothing at all, in the sense that gold was the heaviest commonly known metal. If you take a block of platinum and plate it on the outside with a thin layer of gold, you get an object that is, to the naked eye, indistinguishable from solid gold. More than that, it is nearly indistinguishable by weight. Gold is so close in density to platinum that the difference, for a small bar or coin, is within the margin of error for the scales available at the time. In an era when the entire international financial system was built on the gold standard, when the value of every currency, every debt, every contract ultimately rested on the assumption that gold was gold and could not be faked, platinum was an existential threat. If Wollaston published his refining process, if the knowledge spread, If even a handful of sophisticated criminals or foreign powers got access to refined platinum in quantity, the gold standard could be undermined. Not immediately, not obviously, but systematically, over years, as fake gold bars accumulated in bank vaults and national treasuries, the foundations of the global economy could be quietly rotted from within. Wollaston understood this. He chose very deliberately to sit on his discovery and protect the world from it, while profiting handsomely from the platinum laboratory equipment he was selling to the very scientists who were trying to figure out the secret he was keeping. It was, by any measure, one of the most audacious acts of scientific secrecy in history. He finally published his methods in 1828, shortly before his death, when the development of other analytical techniques had made the counterfeiting threat somewhat less acute. By then, platinum had found its place in the world of science, not as a danger, but as an indispensable tool. The lesson was not lost on the scientists who came after him. Platinum was not just difficult, it was not just rare, it was not just valuable. It was dangerous in the right hands, in the right context. It was a secret that a smart man kept for 20 years because he understood, perhaps better than anyone else of his era, what kind of power a material can carry when the world does not yet know how to handle it. There is a basement in the suburbs of Paris, in a quiet, unremarkable town called Sèvres, where something sits in a vault behind 3 separate locks, under 3 separate keys held by 3 separate people, none of whom are permitted to open it alone. The room has controlled humidity, controlled temperature, controlled everything. And inside it, under bell jars of hand-blown glass nested inside one another like Russian dolls, sits a small metal cylinder. It is about the size and shape of a standard computer mouse. It weighs exactly 1 kilogram. Or rather, and this is where things get philosophically disturbing, in a way that should genuinely unsettle you, it does not weigh 1 kilogram. It is 1 kilogram. It is the kilogram. From 1889, when the International Bureau of Weights and Measures enshrined it as the global standard, until 2019, the definition of 1 kilogram was not a mathematical formula, not a physical constant, not an equation you could derive from the laws of nature. The definition was simply, whatever this object weighs, le grand K, the big K, a cylinder of 90% platinum and 10% iridium, cast in London in 1879, polished to a mirror finish, and thereafter treated with more physical reverence than almost any object in the history of science. 40 copies were made, official replicas, distributed to nations around the world so that each country could calibrate its own scales and instruments against the international standard. The copies were checked against the original every 40 years or so, brought back to Sèvres in a ceremony of almost religious solemnity, placed on ultra-precise balances and compared to le grand K to the nearest fraction of a microgram. And here is where the story stops being a curiosity and starts being a crisis. When scientists began doing those comparisons with the precision available in the 20th century, they found something that nobody could explain and nobody could fix. The copies in the original did not match. Not wildly. We are talking about discrepancies measured in tens of micrograms, which is roughly the weight of a single grain of fine sand. But in metrology, in the science of measurement, a grain of sand is an abyss. Because the question that discrepancy raises is unanswerable by definition. If the copy and the original disagree, which one is right? The original is right, by definition. That is what it means to be the standard. Le grand K weighs exactly 1 kilogram because 1 kilogram means what le grand K weighs. If le grand K gains an atom, then every kilogram in the world has just gotten heavier. If it loses an atom, if a microscopic flake peels away during cleaning, if a molecule of atmospheric contamination bonded to its surface and then detached, then every kilogram in the world has just gotten lighter. And nobody would know. Not the pharmacist measuring out your medication, not the engineer calculating the load-bearing specifications for a bridge, not the scientists running particle physics experiments that depend on precise mass measurements. The entire world's system of mass measurement was anchored to an object that was, by the best available evidence, slowly and invisibly drifting. Imagine standing on what you believe to be solid ground, and then discovering that the ground itself is not fixed, that it rises and falls by imperceptible amounts, randomly, without pattern, and that every measurement you have ever taken relative to that ground is therefore uncertain in a way you cannot quantify. That was the situation with Le Grand K, and the cylinder just sat there in its basement in Sèvres, indifferent as only platinum can be indifferent. While the First World War killed 20 million people, Le Grand K sat in its vault. While the Second World War burned across 3 continents, Le Grand K sat in its vault. While humanity split the atom, walked on the moon, built the internet, sequenced the human genome, Le Grand K sat in its vault, losing or gaining atoms at a rate that nobody could track, anchoring the world's measurement system with the quiet, maddening stubbornness of a thing that does not know it is important. The scientists who oversaw it were not fools.
They understood the problem perfectly well. What they lacked for most of the 20th century was a solution.
To replace a physical standard with a mathematical one, to define the kilogram through a fundamental constant of nature rather than through an artifact, you need to be able to measure that constant with sufficient precision. The particular constant relevant to mass is Planck's constant, the fundamental quantum of action that underlies all of quantum mechanics. Measuring Planck's constant precisely enough to replace Le Grand K required decades of painstaking experimental work, multiple independent approaches, and an international consensus process that moved with all the brisk efficiency of a committee trying to agree on a restaurant. But they got there. On the 20th of May, 2019, the World Metrology Day, which is either charming or nerdy depending on your perspective, the international definition of the kilogram officially changed.
1 kilogram is now defined in terms of Planck's constant, expressed in units of joule seconds. The definition is permanent, universal, derivable from the laws of physics anywhere in the universe, and immune to the slow atomic drift of a metal cylinder in a Parisian basement. Le Grand K was retired. It still sits in its vault in Sèvres, behind its 3 locks and its nested bell jars. It is no longer the definition of anything. It is now just a very expensive, very well-protected, historically significant cylinder of platinum-iridium alloy, sitting in the dark, indifferent to its own demotion. But there is something in that image that lingers long after the technical details fade. For 130 years, the weight of a kilogram, the weight of every kilogram, everywhere in the world, was whatever that small platinum cylinder decided it was. The fate of global measurement rested not on mathematics, but on the physical stability of a piece of metal. And that metal held. Imperfectly, mysteriously, with microscopic deviations that scientists are still arguing about, but it held. It served. It sat in its basement through wars and revolutions and the entire arc of modern civilization, and it kept the world's scales more or less honest. That is not nothing. That is, in its own quiet way, extraordinary. And when they finally freed measurement from its dependence on physical objects, when they finally cut the cord and anchored the kilogram to the permanent bedrock of quantum physics, the cylinder they freed themselves from was platinum. Of course it was. Because platinum, as you are beginning to understand, is not just a material. It is a philosophical statement about permanence, about resistance to change, about the difference between what endures and what merely lasts. Le Grand K is retired. Platinum is not. Let me ask you something personal. Did you eat today? Not a loaded question, not a trick. Just a simple fact of your morning. Coffee, maybe. And something that involved grain. Bread, perhaps, or oatmeal, or a bowl of cereal shaken from a cardboard box and drowned in cold milk. Something common, something ordinary. Something you almost certainly did not think about as you ate it, because why would you? Food is food. Eating is eating. It is the most ancient, most universal human experience, the one constant that connects you to every human being who has ever lived, from the first Homo sapiens picking berries on the African savanna to the astronauts eating rehydrated meals in orbit above your head right now. Here is what I want you to hold on to as we move through this chapter. That bowl of cereal, that piece of toast, that handful of grain. It exists in part because of platinum. And not in some vague, metaphorical, everything is connected to everything else sort of way. In a direct, physical, chemical, no platinum means no food sort of way that becomes absolutely terrifying once you see the numbers clearly. To understand why, we have to talk about nitrogen. Nitrogen makes up 78% of the air you are breathing right now. It is, by volume, the dominant component of Earth's atmosphere. In one sense, we are swimming in nitrogen. We breathe it in and out with every breath of our lives without using a single molecule of it. And yet, in another sense, nitrogen is the one thing that limits all life on Earth. Because while nitrogen is everywhere in the air, almost nothing in nature can use atmospheric nitrogen directly. To become biologically useful, to become part of an amino acid, a protein, a DNA molecule, a living cell, nitrogen atoms need to be bonded to hydrogen atoms to form ammonia, or to oxygen atoms to form nitrates. This process of taking inert atmospheric nitrogen and converting it into biologically active forms is called nitrogen fixation. And for most of the history of life on Earth, it was done almost exclusively by specialized bacteria. A small number of bacterial species have the enzymatic machinery to break the extraordinarily strong triple bond of nitrogen gas and stitch the nitrogen atoms into ammonia. These bacteria live in the soil and in the root nodules of certain plants like legumes, and they are ultimately responsible for the fertility of every field that has ever been farmed. The problem is that natural nitrogen fixation is slow, painstaking, limited. The rate at which natural bacterial processes can fix nitrogen into a form that growing crops can actually use is far below what is required to feed a planet of 8 billion people. For most of human history, this was the fundamental ceiling on agricultural productivity. You could improve your seeds, you could irrigate, you could plow more carefully and rotate your crops and let fields lie fallow, and every improvement helped at the margins. But ultimately, the amount of food a piece of land could produce was constrained by the amount of biologically available nitrogen in that land's soil. And in a world without synthetic fertilizer, that constraint killed. Not abstractly, not eventually, by famine, by crop failure, by the grinding chronic malnutrition that stunted children and shortened lives and made the average human being of the 18th century considerably smaller, sicker, and shorter-lived than the average human being of today. Then, in the first decade of the 20th century, two German chemists, Fritz Haber and Karl Bosch, solved the problem. They devised a process for taking atmospheric nitrogen, combining it with hydrogen at high temperature and high pressure, and producing ammonia synthetically, in industrial quantities. The Haber-Bosch process, as it became known, is probably the most consequential chemical engineering achievement in human history. More humans are alive today because of that process than because of any medical advance, any agricultural improvement, any political revolution. It is not even close. By some estimates, roughly half of the nitrogen atoms in the proteins in your body right now passed through an industrial ammonia plant at some point in the past century. You are, in a very literal biochemical sense, partly a product of industrial chemistry. Now here is where platinum re-enters the story, and re-enters it at a scale that should make you stop breathing for a moment. The Haber-Bosch process produces ammonia, but ammonia is only the first step. To make the nitrogen fertilizers that fields actually use, nitrates, the form of nitrogen that plant roots can absorb, the ammonia needs to be oxidized. It needs to be converted to nitric acid through a process called catalytic oxidation. That process, developed by Wilhelm Ostwald, who won the Nobel Prize in Chemistry in 1990 for it, runs over a catalyst. Specifically, it runs over a gauze of platinum-rhodium alloy wires, heated to somewhere around 900 degrees Celsius, through which the ammonia gas flows and is catalytically converted into nitric oxide, the first step on the road to nitric acid and nitrogen fertilizer. Remove the platinum gauze and the Ostwald process stops. If the Ostwald process stops, nitric acid production stops. If nitric acid production stops, nitrogen fertilizer production stops. If nitrogen fertilizer production stops, not gradually, not over decades, but suddenly, immediately, agricultural yields around the world collapse. The estimates vary depending on the study and the assumptions, but the general consensus among agricultural scientists is that without synthetic nitrogen fertilizer, the Earth's soils can sustainably support somewhere between 3 and 4 billion people. The current global population is approximately 8 billion. That gap, 4 billion people, roughly the population of the entire world in 1975, exists in very significant part because of the catalytic chemistry that platinum enables. Look at it this way. The platinum gauze in a nitrogen fertilizer reactor is not jewelry. It is not a status symbol. It is not an investment vehicle. It is infrastructure. It is as fundamental to the survival of modern civilization as water treatment plants and electrical grids. It is just invisible. Nobody photographs it. Nobody posts about it. Nobody writes songs about it. It sits in its reactor vessel at 900 degrees, doing the same thing it has been doing for over a century, converting ammonia to nitric oxide millions of times per second. In every country that produces food commercially, without recognition and without rest. There is a particular kind of cognitive dissonance in contemplating this fact while sitting in a grocery store, surrounded by the extraordinary abundance of the modern food supply. Every loaf of bread on that shelf, every bag of rice, every carton of eggs from chickens fed on grain that grew in fields fertilized with synthetic nitrogen. Every vegetable, every fruit, every processed food that contains grain-derived ingredients, all of it traces a supply chain that passes, at some point, through the catalytic surface of a platinum gauze heated to 900 degrees in an industrial reactor somewhere in the world. You are not just wearing asteroid shrapnel on your finger, you are eating it, metabolizing it, incorporating its catalytic influence into your own biochemistry, one nitrogen atom at a time. The conquistadors threw platinum in the river because they thought it was garbage. We've arranged it so that without platinum, half of us would starve. Let us go to London. Not the London of today with its underground map and its coffee shops and its 7.5 million people going about their days in the ordinary, controlled chaos of a modern metropolis. Let us go to London in December of 1952. More specifically, let us go to London in the 5 days between the 4th and the 9th of December 1952, which are 5 days that the people who lived through them never forgot, and which anyone who studies the history of environmental policy will tell you changed the world. The weather that December had been cold and still for weeks. Londoners had responded the way Londoners always responded to cold weather in that era, by burning coal. Coal in their home fireplaces, coal in the power stations, coal in the industrial facilities that ringed the city. London in 1952 still ran on coal the way a living creature runs on oxygen. It was the fuel of the empire, the heat of the home, the engine of industry. And on the 4th of December, the weather conditions conspired against the city in a way that the city was completely unprepared for. A high-pressure system settled over southern England and refused to move. The air became perfectly, lethally still. There was no wind to carry the coal smoke away from the city. There was no atmospheric mixing to dilute it. Instead, a thermal inversion formed, a layer of warm air trapping cold air near the ground. And all of London's coal smoke, all of its industrial exhaust, all of its vehicle emissions had nowhere to go. They just stayed. They accumulated. They mixed with the natural river fog that the Thames had been producing for centuries, and they created something that was not quite fog and not quite smoke, but was something far more dangerous than either. It turned yellow-green. It blocked the sun so completely that in some parts of the city, visibility dropped to a few feet. People walked into lampposts. Buses had to be led through intersections by conductors walking in front of them with flashlights. Indoor performances were canceled because the audience could not see the stage through the smog that had seeped in through every gap and crack in the building. And people started dying. The hospitals filled, the morgues filled. The death toll in those 5 days was somewhere between 4,000 and 12,000 people. The estimates vary depending on how you count the deaths that occurred in the weeks following from lung damage, with most victims dying from acute respiratory failure, their airways overwhelmed by sulfur dioxide and nitrogen oxides and particulate matter in concentrations that should never be possible in a city where human beings live. The Great Smog of London, that is what they called it. And in its aftermath, the British government did something that governments rarely do with the speed and decisiveness that the scale of the problem demanded. They legislated. The Clean Air Act of 1956, restrictions on coal burning in residential areas, requirements for taller industrial chimneys to disperse emissions above the inversion layer. The beginning, however slow and painful and politically contested, of modern air quality regulation. But legislation only goes so far. Because even if you ban coal in home fireplaces, you still have the cars. By the 1960s, by the 1970s, the automobile had become as fundamental to modern life in wealthy countries as coal had been to Victorian London. And the internal combustion engine, for all its extraordinary utility, produces exhaust that is a chemical nightmare. Carbon monoxide, a colorless and odorless gas that bonds to hemoglobin in your blood and prevents it from carrying oxygen, causes unconsciousness and death in enclosed spaces at surprisingly low concentrations. Hydrocarbons, unburned fuel fragments that react with sunlight to form ground-level ozone and the brown photochemical smog that settled over Los Angeles in the 1950s and 60s so reliably that people learned to schedule their outdoor activities around it. Nitrogen oxides, the same family of compounds that helped create London's Great Smog, formed at the high temperatures inside internal combustion engines and released directly into the air you breathe at street level. Without intervention, the growth of the global automobile fleet would have reproduced the Great Smog of London and every major city in the industrialized world, every day, indefinitely. It would have been a slow catastrophe rather than a sudden one. Instead of a 5-day event that killed 12,000 people, it would have been a chronic background condition that shortened the lives of hundreds of millions. The intervention that prevented this is sitting in the exhaust system of almost every car built after 1975. The catalytic converter. A device that, from the outside, looks like an unremarkable canister wedged into a car's exhaust pipe. Inside, it is something considerably more elegant, a ceramic honeycomb structure with a surface area, if you were to unfold all its microscopic channels and lay them flat, comparable to that of a football field, coated with a thin layer of precious metals, platinum, palladium, and rhodium. On that catalytic surface, at the operating temperature of the exhaust stream, 3 distinct reactions occur simultaneously. Carbon monoxide is oxidized to carbon dioxide. Unburned hydrocarbons are oxidized to carbon dioxide and water. Nitrogen oxides are reduced to pure nitrogen gas. The toxic cocktail that enters the catalytic converter becomes, as it exits, mostly water vapor and carbon dioxide. Not harmless exactly, but orders of magnitude less immediately dangerous than what went in. The amount of platinum in a typical catalytic converter is somewhere between 3 and 7 grams. 3 to 7 grams, less than 1/4 of an ounce. That is all. That thin microscopic coating on the inner surface of that ceramic honeycomb, enough platinum to cover, if stretched thin enough, a surface the size of a football field, is what stands between the exhaust output of the world's 1.5 billion internal combustion vehicles and the air that the people in the streets those vehicles drive through are breathing. Now I want you to perform a thought experiment with me. Imagine that catalytic converters simply stop working. Not gradually, immediately. Every car on the road, every truck, every bus, every motorcycle, every piece of construction equipment with an internal combustion engine. All of them, starting tomorrow morning, producing unfiltered exhaust, putting out full, unmitigated concentrations of carbon monoxide, hydrocarbons, and nitrogen oxides into the air of every city on Earth. The effects would not take years to appear. They would take days. Major urban centers, cities where traffic density is high, where people live and work close to busy roads, where atmospheric mixing is limited, would begin registering air quality readings within a week that would trigger mandatory evacuation orders under current environmental regulations. The nitrogen oxides, in the presence of atmospheric moisture, would begin forming nitric acid, which falls as acid rain, stripping nutrients from soil and killing aquatic life in rivers and lakes downwind of population centers. The ground-level ozone formed from hydrocarbon photochemistry would devastate agricultural crops across entire regions. Ozone is, after all, one of the most potent plant toxins that exists at ambient concentrations. Within a few months, respiratory disease rates in cities would begin tracking toward the numbers seen in the industrial cities of the early 20th century. The chronic lung disease, the elevated cancer rates, the shortened life expectancies that we associate with the Victorian era of coal, all of that would begin reasserting itself. All because of 3 to 7 grams of precious metal per vehicle gone. The catalytic converter is one of the most successful public health interventions in human history. It has, by various estimates, prevented millions of premature deaths since its widespread adoption in the 1970s and 80s. It did this not through legislation, not through behavior change, not through any sacrifice on the part of drivers, but through chemistry. through the catalytic surface chemistry of platinum and its sister metals, working silently and continuously in the exhaust stream of every car you have ever ridden in. And that platinum, those few grams that guard the air of your city, eventually wears. Not quickly, not in a single dramatic failure, but over the life of a vehicle, as the exhaust stream flows through millions of times, microscopic flakes of catalyst erode and exit through the tailpipe, dispersing into the road dust that accumulates at the edges of highways, that blows into the verges and the storm drains and the soil of every neighborhood where traffic runs. The platinum that came from an asteroid 4 billion years ago, that was forged in a neutron star collision billions of years before that, has been slowly redistributed, atom by atom, into the roadside dust of the 21st century. Perhaps the conquistadors were not wrong about one thing. Platinum does end up where it does not seem to belong. The difference is that now we understand what it was doing there. It is 1965. A university laboratory at Michigan State, the kind of space that looks unremarkable to everyone except the people working in it. Benches crowded with glass and wire and tubing, the smell of agar and disinfectant, the particular quiet of a room where people are concentrating hard on small things. Barnett Rosenberg is a biophysicist, not a chemist, not a physician, a biophysicist, which means he is interested in the places where physics and living systems intersect, in the electrical properties of cells, in what happens when you apply electromagnetic fields to biological processes. His experiment on this particular day is modest in its ambition. He wants to observe the effect of electric current on the growth and division of bacteria, specifically Escherichia coli, the workhorse microorganism of biological laboratories everywhere. A bacterium that under normal conditions divides roughly every 20 minutes, with the relentless, cheerful efficiency of something that has been perfecting cell division for 3 billion years. He needs electrodes to run current through his bacterial culture, and for electrodes, he chooses platinum. The choice is almost automatic, the kind of decision that does not get written down because it barely rises to the level of conscious thought. Platinum is inert. That is the whole point of platinum in an experimental context. It does not react. It does not dissolve. It does not contaminate your sample with metal ions that might confuse your results. Platinum is the transparent window through which you apply electricity without introducing chemistry. It is the perfect null material. The experiment begins. The current flows through the platinum electrodes into the bacterial culture, and the bacteria stop. Not immediately, not completely, but something goes profoundly wrong with the way they are dividing. The cells do not die, not at first. They continue growing, extending, elongating, but they stop splitting. Under the microscope, Rosenberg sees Escherichia coli cells that are hundreds of times longer than they should be. Vast, grotesque filaments that look nothing like the neat, short rods of a normal bacterial culture. The cells are alive, they are metabolizing, consuming nutrients, building proteins, but the fundamental act of biological reproduction, the moment when one cell pinches in the middle and becomes two, is not happening. It is as though someone has found the circuit breaker for cellular division and switched it off. Rosenberg is a good scientist, which means his first response to a puzzling result is not to celebrate or to explain, but to check his assumptions. He runs the experiment again without current. The bacteria behave normally. He changes the electrodes to carbon and runs the experiment again with current. The bacteria behave normally. He goes back to platinum electrodes. The bacteria stop dividing again. Something about the combination of platinum and electrical current is shutting down cell division in bacteria. The obvious hypothesis, the one that took several more months to confirm through careful chemical analysis, is that the current is causing the platinum to dissolve slightly, releasing platinum compounds into the culture medium. Compounds that are then interacting with the bacteria in some way that interferes with their ability to reproduce. He identifies the specific compound responsible. It is a molecule called cis-diamine dichloroplatinum, a relatively simple coordination compound in which a platinum atom sits at the center, bonded to 2 ammonia groups and 2 chloride atoms, all arranged on the same side of the molecule, the cis configuration, as opposed to the trans configuration in which they sit on opposite sides. Cisplatin. The name is almost trivially simple for something that will turn out to be one of the most consequential molecules in the history of medicine. Rosenberg begins testing it on tumor cells. He is not an oncologist. He does not have a clinical research program. He does not have funding for cancer research. But he has results that are difficult to ignore. Results suggesting that this platinum compound does to cancer cells what it did to his bacteria, and does it with a specificity and potency that the existing cancer drugs of the 1960s cannot match. The mechanism, when it is finally fully worked out over the following decade, is one of the most elegant pieces of molecular sabotage in all of biochemistry. When a cisplatin molecule enters a cell and encounters the aqueous environment of the cellular interior, the chloride atoms partially detach, making the platinum atom more chemically reactive. That reactive platinum atom then does something specific and devastating. It inserts itself between the two strands of the DNA double helix and forms what chemists call a crosslink, a covalent bond that physically staples the two strands of the DNA molecule together or bends them into a kink that makes the molecule unreadable. Cancer cells, like all rapidly dividing cells, need to copy their DNA constantly. Every time a cancer cell prepares to divide, it needs to unzip the double helix, read each strand as a template, and synthesize a new complementary strand. This is the most fundamental act of biological reproduction, and it requires that the DNA strands be free to separate and be read. A cisplatin crosslink prevents this. The cell cannot unzip its DNA. It cannot read the template. It cannot make the copy. And when a cell cannot complete DNA replication, it cannot divide. The cellular machinery that monitors DNA integrity detects the crosslink as damage, recognizes that replication has stalled, and initiates a cascade of signals that ends, if the damage is severe enough and the cell's repair mechanisms cannot fix it, in what biologists call apoptosis, programmed cell death. The cell, following instructions embedded in its own genome, dismantles itself in an orderly and contained way, not bursting open and spilling its contents to cause inflammation, but quietly dissolving itself into fragments that nearby immune cells can absorb and recycle. The cancer cell, in other words, receives a command to commit suicide, and it obeys. The preference of cisplatin for rapidly dividing cells, because those are the cells most urgently trying to copy their DNA at any given moment, gives it a selectivity for tumors over normal tissue that, while imperfect, makes it far more useful as a drug than a simple cellular toxin would be. It damages normal cells too. The side effects of cisplatin treatment, nausea, kidney damage, hearing loss, the loss of hair that has become the visual shorthand for chemotherapy in popular culture, are the signature of that collateral damage. But in certain cancers, the ratio of tumor cells killed to normal cells killed is favorable enough to make it a viable, even a transformative treatment. The numbers tell the story more clearly than any description can. Testicular cancer, one of the most common cancers in young men, a cancer that strikes people in their 20s and 30s at the height of their lives, had a mortality rate of roughly 90% in the era before cisplatin. 9 in 10 men diagnosed with testicular cancer in the 1960s would die from it. After the widespread adoption of cisplatin-based chemotherapy regimens in the late 1970s and 1980s, the survival rate inverted. Today, approximately 95% of men diagnosed with testicular cancer survive it. The same disease, the same patients, the same diagnosis that was, within living memory, nearly a death sentence, transformed into something that the majority of people who receive it will survive and recover from fully. Cisplatin and its chemical descendants are now used against cancers of the ovary, the bladder, the lung, the head and neck, a family of platinum-based drugs that collectively treat a significant fraction of all cancer patients who receive chemotherapy anywhere in the world. The platinum in those drugs is the same platinum that was forged in a neutron star collision. It is the same platinum that the conquistadors threw into a Colombian river. It is the same platinum that William Wollaston refined in secret to protect the gold standard. It traveled through space, through geological time, through the hands of soldiers and scientists, through laboratory accidents and decades of clinical trials, and it arrived, finally, in the bloodstream of cancer patients in oncology wards in hospitals on every inhabited continent, carrying out, at the molecular level, the most precise possible version of the mission that things have always used platinum for. holding on and not letting go. A platinum atom stapled to the DNA of a cancer cell is not complicated. It is not advanced. It is just a small, very stable piece of star stuff, doing what platinum has always done since the moment it was forged at the collision of two dead stars, refusing to release what it has caught hold of. The conquistadors called it garbage. Oncologists call it a miracle. The platinum does not care what you call it. It just holds. Let us talk about what it actually takes to get platinum out of the ground. Not in the abstract, not in the sanitized language of annual reports and investor presentations, but in the real, physical, geological, human sense of what it means to pull this metal from the earth and deliver it to the world that depends on it. Because there is a gap, a vast, almost surreal gap, between the platinum you know and the process that produces it. On one side of that gap, a wedding ring, a catalytic converter, a hospital IV drip carrying cisplatin into the bloodstream of a cancer patient. Clean, purposeful, precise. On the other side, one of the largest, loudest, most violent industrial operations on the surface of the planet. To get from one side to the other, you need to move 10 tons of rock for every single ounce of platinum you want to produce. Not 10 tons for a kilogram, not 10 tons for a pound. 10 tons, 22,000 pounds of solid rock for 31 grams of metal. An ounce. An amount you could balance on a kitchen scale alongside a small handful of paper clips. That is the extraction ratio for platinum. That is the fundamental geological reality of the most platinum-rich mining district on Earth, which is a place called the Bushveld Igneous Complex in South Africa. And it is, by any measure, one of the most extraordinary geological formations on the planet. The Bushveld Complex is large. When you look at it on a map, it covers an area roughly comparable to the island of Ireland, a roughly oval scar of ancient igneous rock stretching across the interior of South Africa's Limpopo and Northwest provinces, formed approximately 2 billion years ago when an enormous quantity of magma welled up from the mantle and intruded into the existing continental crust. As that magma slowly cooled over millions of years, the different minerals in it crystallized out in sequence, settling into distinct layers, a process called magmatic layering that produced a kind of geological layer cake with different minerals concentrated at different depths. Platinum group metals, being dense and having specific chemical affinities, concentrated into particular layers of that cake. The most important of these is called the Merensky Reef, named after Hans Merensky, the geologist who identified it in 1924. The Merensky Reef is not a dramatic geological feature. If you could see it from the outside, if you could strip away the overlying rock and look at it directly, it would not look impressive. It is a layer of rock, typically between 30 centimeters and 1.5 meters thick. In a geology of continental proportions, it is a whisper, a seam, barely a line. But that line, traced through the rock for hundreds of kilometers, contains the largest known concentration of platinum group metals on the surface of this planet. Somewhere between 70 and 80% of the world's known platinum reserves lie in that one narrow reef, which means that to access the metal that keeps the world's catalytic converters functioning, that enables the production of nitrogen fertilizer, that treats cancer and defines the kilogram, and fills the world's jewelry cases, you have to go down into the earth and cut that whisper of rock out of the geological cake it has been embedded in for 2 billion years. The mines of the Bushveld complex go deep. Some of them reach 2 kilometers below the surface. 2 kilometers is not just a number. It is a physical reality that changes everything about the experience of being there. At 2 kilometers below the surface, the rock temperature is not the ambient temperature of a cool underground space. It is 40 degrees Celsius or more, the heat of the Earth's interior radiating outward through the surrounding rock, turning the mine tunnels into humid, oppressive corridors where working without cooling systems would be physiologically impossible. The Merensky Reef, being less than 1.5 meters thick in most places, cannot be accessed by the large mechanized excavation equipment that makes modern mining operations efficient. The seam is too thin. To get at the platinum-bearing rock without wasting enormous quantities of processing resources on the barren rock surrounding it, miners have to go in and work the reef manually, drilling blast holes along the face of the reef, placing explosives, retreating, detonating, and then returning to clear the broken rock and advance the face another meter or two. In some sections, the working height in the stope, the excavated cavity where the miners actually work, is less than a meter, less than 3 feet. Which means that the work of extracting the most valuable metal deposit on Earth is done by human beings lying on their sides in 40-degree heat, a kilometer or more below the surface, handling tools in a space where they cannot stand up. The broken ore, those 10 tons per ounce, gets hauled to the surface and transported to processing facilities that look, from the outside, like small industrial cities. The ore is crushed again, ground to a fine powder in massive rotating mills. The powder is mixed with water and chemical reagents in flotation tanks, where the platinum-bearing minerals attach to air bubbles and float to the surface as a concentrate, a step that reduces the volume significantly but is only the beginning of the separation process. The concentrate goes to a smelter, where it is heated to temperatures that would vaporize most metals, and the platinum group metals are collected in a molten iron sulfide phase, a matte, that is then cast into blocks and sent for further refining. The refining process separates not just platinum from the surrounding rock, but platinum from the other platinum group metals that occur alongside it: palladium, rhodium, iridium, osmium, ruthenium, each of which has its own chemical properties and its own industrial applications and its own separate market. The full process, from ore in the ground to refined platinum in a bar, typically takes between 6 and 18 weeks. 6 to 18 weeks to move 31 grams of metal from the reef to the surface and separate it from everything that is not it. Now let us look at the numbers from a different angle. Zoom out. Pull back from the individual mine, from the individual kilogram of ore being processed on this particular day, and look at the totality of what human civilization has ever managed to extract. All the gold ever mined in human history, from the tombs of Egyptian pharaohs to the California gold rush to the mines of today, is estimated at around 210,000 metric tons. An enormous amount, seemingly. But if you were to gather it all together in one place and cast it into a solid cube, that cube would measure roughly 22 meters on each side, less than the length of a standard swimming pool. A modest office building could contain all the gold humanity has ever extracted from the Earth. The total amount of platinum ever mined in human history is considerably less than that. The best estimates put the total historical production of platinum at somewhere around 8,000 metric tons. A cube with sides of roughly 3.5 meters. A large garden shed. You could fit everything humanity has ever refined and used. Every catalytic converter, every piece of platinum jewelry, every laboratory crucible, every kilogram standard cylinder, every gram of cisplatin inside something the size of a large garden shed. And current annual production is roughly 180 to 200 metric tons per year. 180 tons for the entire planet. For all its cars and all its factories and all its hospitals and all its research laboratories and all its jewelry stores. The entire global supply of newly mined platinum in a year would fit inside a room you could rent for a wedding reception. Every gram of it extracted at the cost of 10 tons of rock, weeks of processing, and the labor of human beings working in conditions that would fail every occupational health standard in the developed world if those standards were applied consistently to the supply chains of the products that depend on them. There is a word that economists use for this situation, for when the supply of something critical to a system is both small and geographically concentrated, and difficult to increase quickly. The word is vulnerability. South Africa produces roughly 70% of the world's platinum. Russia, primarily through a single company operating in the Norilsk region above the Arctic Circle, produces most of the remainder. 2 countries, 2 mining regions, 1 extraordinarily thin reef of ancient igneous rock formed 2 billion years ago by a geological accident that could as easily have not happened. That is the supply chain for the metal that holds half of humanity's food supply in its catalytic grip, that cleans the air of every major city, that treats cancer, that defined the kilogram. 1 reef, 10 tons of rock per ounce, 6 to 18 weeks of processing. 2 countries. This is not a system that was designed. It is a system that evolved, one discovery and one application at a time over 3 centuries, without anyone ever stepping back to ask whether the foundation was adequate to the weight being placed upon it. The conquistadors threw platinum in the river because they could not see its value. We have spent 3 centuries discovering its value in exquisite detail, and we have not yet fully reckoned with how fragile the system is that delivers it. There is a word that has become, in the early decades of the 21st century, something close to a secular prayer for the energy industry. A word that carries the weight of hope and urgency and the particular anxiety of a civilization that has finally, after decades of denial, fully understood what it has been doing to its own atmosphere. The word is hydrogen. Hydrogen fuel. The hydrogen economy. Green hydrogen. The idea, stated simply, is almost disarmingly elegant. Hydrogen is the most abundant element in the universe. When you burn it, or more precisely, when you combine it with oxygen in an electrochemical reaction called a fuel cell, the only exhaust product is water. Pure, clean water vapor. No carbon dioxide, no nitrogen oxides, no particulate matter, no greenhouse gases of any kind. A civilization running on hydrogen fuel would be, from a climate perspective, exactly the kind of civilization that the physics of the atmosphere is demanding that we build, as quickly as possible, before the carbon dioxide already in the air commits us to temperature increases that will make the world we know unrecognizable. The excitement around hydrogen as a transportation fuel and an energy storage medium has been building for decades, but it accelerated sharply in the late 2010s and early 2020s as the costs of renewable electricity fell dramatically, and as the window for meaningful climate action narrowed to the point where dramatic technological shifts stopped seeming like futurism and started seeming like necessity. Governments began announcing hydrogen strategies. Corporations began announcing hydrogen investments. The phrase green hydrogen economy began appearing in policy documents with the frequency that blockchain had appeared in tech investment memos a few years earlier. Sometimes with more justification, but with a similar mixture of genuine promise and wishful thinking. And inside all of this excitement, inside the technical specifications and the engineering diagrams and the pilot plant proposals, there is a quiet, stubborn fact that tends to get mentioned in footnotes and technical appendices rather than headlines. The type of fuel cell best suited for mobile applications, for cars, for trucks, for buses, for the transportation sector that currently produces a substantial fraction of global carbon emissions, is called a proton exchange membrane fuel cell, a PEM fuel cell. And a PEM fuel cell requires platinum, not as a trace component, not as a minor ingredient that could perhaps be engineered away given enough research and development funding and time, as a fundamental catalyst, sitting at the core of the device, enabling the electrochemical reactions that make the whole thing work. In a PEM fuel cell, hydrogen gas enters one side of the device and contacts a platinum catalyst at what is called the anode. The platinum catalyst strips electrons from the hydrogen molecules, creating protons, positively charged hydrogen ions, that migrate through a polymer membrane to the other side of the device. The electrons, unable to cross the membrane, travel through an external circuit, doing useful electrical work, powering the motor, driving the wheels, before rejoining the protons and oxygen at the other electrode, the cathode, where another platinum catalyst facilitates the combination of protons, electrons, and oxygen to produce water. Take away the platinum catalyst and the reaction rates drop by orders of magnitude. The fuel cell becomes too slow to be practical. The platinum at both electrodes is not optional in the sense that it could be replaced with something cheaper if only we had the engineering will to find an alternative. It is not optional in the sense of not having found the right substitute yet. It is, based on everything currently known about electrochemistry, central to the efficiency and durability of PEM fuel cells at the operating conditions, temperature, pressure, current density, required for commercial transportation applications. Researchers around the world are working on reducing the amount of platinum required per fuel cell, and they have made meaningful progress. The platinum loading in a state-of-the-art PEM fuel cell today is considerably lower than it was 20 years ago. But reducing is not eliminating. And when you take the amount of platinum currently required per fuel cell and multiply it by the scale of the hydrogen economy that climate policy demands, you arrive at a number that collides head-on with the supply reality we examined in the previous chapter. The International Energy Agency has estimated that meeting global climate targets through a significant expansion of hydrogen fuel cell vehicles would require roughly doubling current platinum demand from the automotive sector alone, on top of existing uses. Some more aggressive scenarios require significantly more than that. Remember the garden shed. Remember the 180 tons per year. Remember the one reef in South Africa, the one region in Russia, the 10 tons of rock per ounce, the 6 to 18 weeks of processing. The arithmetic is uncomfortable. We are proposing to build a new energy system that depends on a material that the Earth's crust provides in quantities measured in hundreds of tons per year, that comes predominantly from 2 countries, and that we have spent 3 centuries developing applications for, without ever seriously asking whether the supply could be scaled. This is not an argument against hydrogen fuel cells. They represent genuinely promising technology, and they may play an important role in the energy transition, particularly for applications where battery electric systems are impractical. It is simply the observation that the path from here to a hydrogen economy runs directly through a platinum bottleneck, and that bottleneck is geological, not merely economic. More money will not dissolve it. More research will not eliminate the need for platinum catalysts by next Tuesday. The question of where the platinum comes from is a real question that requires a real answer. And here, at exactly the moment when the story seems most constrained, when the walls of geological reality seem to be closing in from both sides, someone in California has a different idea entirely. His name is not important for this story, but his industry is. He is part of a small but growing community of engineers and entrepreneurs who have looked at the constraints of terrestrial platinum supply and concluded, with the calm confidence of people who have spent too much time around rocket engineers and not enough time around geologists, that the answer to insufficient platinum on Earth is to go and get some from somewhere else: the asteroid belt. Between Mars and Jupiter, in the broad band of rocky debris that represents the leftover material from the formation of the solar system, material that never coalesced into a planet because Jupiter's gravitational influence kept disrupting the process, there are millions of asteroids. Most of them are rocky, undifferentiated rubble of limited commercial interest. But some of them are metallic. Some of them are the cores of ancient protoplanets, small bodies that began the differentiation process, that began separating into iron cores and rocky mantles, and then were shattered by collisions before that process was complete. These metallic asteroids are, in effect, raw planetary cores drifting through space. They were not melted into a planet, so their metals, including their platinum group metals, never sank away. They are still there, distributed throughout the metal matrix, waiting. The asteroid 16 Psyche is the largest known metallic asteroid in the solar system, and it is the one that tends to appear in the press releases of asteroid mining companies and the speeches of space agency administrators when the subject of extraterrestrial resources comes up. 16 Psyche is located in the main asteroid belt at an average distance from the Sun of roughly 2.9 astronomical units, about 430 million kilometers from Earth at its closest approach, give or take. It has a mean diameter of somewhere between 200 and 220 kilometers. It is not a round, smooth object. It is irregular, battered, ancient, a survivor of 4.5 billion years of collisions and gravitational interactions. Its composition, based on radar and spectroscopic observations, is estimated to be predominantly iron and nickel, with significant quantities of other metals, including platinum group elements. The total estimated value of the metals in 16 Psyche has been calculated, and these calculations are inherently speculative, depending on assumptions about composition and concentration that remote sensing can only partially confirm, at figures that range from 10 quadrillion to potentially $100 quadrillion. $100 quadrillion. The total gross domestic product of every country on Earth in a given year is somewhere around $100 trillion. 16 Psyche, if the estimates are anywhere near correct, contains more metal wealth than the entire global economy produces in 1,000 years. The National Aeronautics and Space Administration, NASA, launched a spacecraft in October of 2023 called the Psyche mission. Its purpose is not to mine the asteroid. It is to orbit it, study it, map its surface composition with scientific instruments, and help us understand what it actually is. Because the truth is that while the evidence strongly suggests 16 Psyche is a metallic asteroid, we have never actually confirmed this up close. And the difference between a largely metallic body and a rubble pile with a metallic surface coating makes a rather large difference to anyone planning to extract resources from it. The Psyche spacecraft is currently en route. It is expected to arrive at the asteroid in August of 2029. In the meantime, back on Earth, a handful of startups, some in California, some in Luxembourg, some in other jurisdictions that have passed legislation attempting to establish legal frameworks for space resource extraction, are writing software for autonomous mining systems, designing concepts for resource extraction platforms, and raising money from investors who are either visionaries or believers in very long time horizons, depending on your perspective. The gap between those California offices and the surface of an asteroid 400 million kilometers away is not a gap you close with ambition and venture capital, however plentiful. The engineering challenges of asteroid mining are real, deep, and only partially solved even in concept. But the trajectory of the idea is clear. Humanity began by throwing platinum in a river. Then we refined it in secret to protect the gold standard. Then we used it to define the kilogram. Then we used it to feed half the world and clean the air and treat cancer. And now we are sending spacecraft to metallic asteroids to figure out whether we can go and get more. The gray metal that the conquistadors called garbage has become the thing we are willing to cross the solar system for. That is not nothing. That is, measured in the currency of human ambition, something extraordinary. We slow down now. The story has moved fast, from Colombian jungles to neutron star collisions, from Parisian basements to asteroid orbits. And it has been, deliberately, a story about what platinum does, about what it enables, about the extraordinary chain of consequences that flows from a few grams of a gray metal placed in the right context at the right moment. But there is one more thing about platinum that deserves its own quiet space. Not what it does, what it is. What it is, in the deepest physical sense, when you strip away every application and every historical episode and every piece of financial valuation and simply look at the material itself, sitting on a bench under a light. Platinum does not react with water, not cold water, not hot water, not the slightly acidic water that constitutes most of what flows in rivers and falls from clouds. You could submerge a piece of platinum in the ocean for 1,000,000 years and retrieve it unchanged. Not merely unrusted, unchanged. Not a single atom of its surface would have bonded with the surrounding water or salt or dissolved oxygen in any way that altered its composition or its appearance. Platinum does not react with oxygen at room temperature. This is so basic, so foundational to the identity of the metal, that it is easy to pass over without appreciating what it actually means. Oxygen is extraordinarily reactive. It is the reason iron rusts, the reason copper turns green, the reason silver tarnishes, the reason wood burns, the reason organic molecules break down over time. Oxygen is, chemically speaking, a highly aggressive element that is perpetually seeking electrons to capture. And platinum, exposed to atmospheric oxygen at any temperature you would encounter in normal life on Earth, simply ignores it. The electrons in platinum's outer shells are arranged in a configuration that makes them extraordinarily stable, extraordinarily reluctant to participate in the kinds of chemical exchanges that oxygen is trying to initiate. Oxygen pushes. Platinum does not answer. Platinum does not react with most acids, as the scientists of the 18th century discovered to their frustration. The only substance that dissolves platinum under normal conditions is aqua regia, that smoking mixture of concentrated hydrochloric and nitric acid combined, and even then only slowly, and aqua regia is not something that occurs in nature. The conditions on the surface of the Earth, in the presence of air and water and the full range of biological chemistry that living systems produce, simply do not include anything capable of attacking platinum. This means that a piece of platinum, placed in any environment that could be described as natural or terrestrial, will endure. Not for years, not for centuries, for geological timescales, for millions and hundreds of millions of years, with no meaningful change. Consider what that actually implies. Take your platinum ring, or imagine one if you do not own such a thing. Imagine throwing it into the Mariana Trench, the deepest point in the ocean, 11 kilometers below the surface, under a pressure of more than 1,000 atmospheres, in the cold and the dark. The ring falls. It lands on the sediment at the bottom. Time passes. Not years, centuries. The civilizations that built the ship from which you dropped it rise and fall. Languages go extinct. Species evolve and go extinct. The continents move, slowly but continuously, carried by the convection of the mantle below. Over millions of years, what is now ocean floor is subducted, dragged down into the mantle by the movement of tectonic plates. And new ocean floor is created elsewhere by volcanic activity at mid-ocean ridges. But before that happens, in the 50 or 100 million years that the current configuration of ocean floor persists, the ring lies on the sediment undisturbed, unchanged, not corroded, not dissolved. Not degraded in any way by the water, the pressure, the dark, the absence of oxygen at depth, the presence of biological activity around it, the weight of 11 kilometers of seawater above it. It simply lies there and waits. Now push further. Extend the timeline. The sun, in approximately 5 billion years, will exhaust its hydrogen fuel and expand into a red giant, swallowing the inner planets. Mercury and Venus for certain, Earth quite possibly. The oceans will evaporate long before that, as the sun's luminosity increases over the next billion or 2 years, and the surface temperature of Earth rises past the point where liquid water can persist. The atmosphere will thin and dissipate into space. The surface will become a dead, dry, airless desert of rock, under a sky that has no color because there is nothing to scatter the light. And in that desert, somewhere on what used to be a seafloor, the platinum ring will still be there, unchanged. No rust, no patina. No surface degradation of any kind. Pure platinum metal, sitting on what was once the bottom of the Pacific Ocean, waiting with the absolute patience of something that has never needed anything from its environment and has never been threatened by it. The second law of thermodynamics, entropy, the tendency of all ordered systems to move toward disorder over time, is one of the most fundamental principles in all of physics. It is why ice melts and hot coffee cools and buildings crumble and stars burn out and living things age and die. It is the reason that time has a direction. It is, in some philosophical formulations, the arrow that points from past to future, because entropy increases in one direction and not the other. And platinum, in the conditions that exist on the surface of a planet like Earth, seems to exist in a kind of privileged relationship with entropy. Not outside of it. Platinum can be melted and recast. Its atoms can be rearranged by sufficient energy input. It will eventually be swallowed by a dying sun, along with everything else in the solar system. But in the practical timescales of life on this planet, in the millions of years during which complex chemistry and biology and geology operate, platinum does not participate in the general tendency of things to fall apart. It holds its form. It holds its composition. It holds its identity. Everything around it changes. Platinum does not. Lay this against the human experience of existing in time. We live, at most, a century, and most of us considerably less. We age, our cells accumulate damage, the things we build deteriorate, the languages we speak evolve until they become unrecognizable to their own descendants. The institutions we create rise and fall. The ideas we hold to be permanent truths are revised and sometimes overturned by the generations that follow. We are, as a species, defined by our temporariness, by the fact that everything we are and everything we make is in process, always becoming something else, always decaying at the edges or growing in the center or being replaced by its own successors. We are creatures of time in the deepest sense. Platinum is not. Platinum is a thing that time passes through without touching, and there is something in that, in the confrontation between human temporariness and platinum's absolute stability, that carries a weight beyond chemistry or materials science or even philosophy. We are the ones who found it. We are the ones who understood what it was and where it came from and what it could do. We named it, we refined it, We deployed it in catalytic converters and cancer drugs and kilogram standards and laboratory crucibles. We gave it its role in the human world. Platinum did not seek us out. Platinum did not need us. Platinum would have been perfectly content, if a metal can be said to have preferences, lying in the Mariansky Reef for another 2 billion years, or drifting through the asteroid belt as shrapnel from a dead protoplanet, unchanged through all the remaining history of the solar system. We are the variable in this story. Platinum is the constant, and there is something both humbling and magnificent in that distinction. We began with a soldier and a river. Let us end there, too. Somewhere in the highlands of Colombia, in a year that was probably around 1545 or 1550, a man stood at the edge of a fast-moving river in the heat of a South American afternoon. He was tired. He was malnourished, almost certainly. He had malaria, probably, or had just recovered from it, or was about to get it. Malaria killed conquistadors with the democratic efficiency of something that does not care about rank, valor, or the letters of commission from the Spanish crown you are carrying in your pack. He had crossed an ocean and walked through a jungle and watched colleagues die, and he was here, under this sky, for one reason: gold. And in his hand, heavy and gray and completely unremarkable, was a lump of platinum. He turned it over once, maybe, looked at it. It told him nothing. It had no gleam, no warmth, no promise. It was not gold. It was not silver. It was a gray, dense, stubborn, ugly rock that behaved wrong in fire and resisted every tool he knew how to apply to it. He flicked it into the river. It disappeared into the current without ceremony. That man is dust now. His name is not recorded. The specific riverbed where he stood has been reshaped by 470 years of floods and sediment and the slow movement of the land. The empire he served no longer exists. The entire framework of thought within which he operated, the theology, the political philosophy, the metallurgy, the cosmology, has been replaced so thoroughly that a person of his era, transported to the present, would be more disoriented than a visitor from another planet. Everything about that moment has dissolved into time. Except the platinum. The platinum that he threw in the river is still platinum. If it were retrieved, if by some archaeological miracle a sample of those colonial-era riverbed sediments were found and analyzed, the atoms would be identical to what they were when he held them. The same atoms that were forged in a neutron star collision billions of years before the solar system formed. The same atoms that drifted through the early solar system and were swept up into the asteroid that struck the young Earth during the late heavy bombardment. The same atoms that lay in the Mariansky Reef and were washed into the river systems and found their way into the gold-bearing sands that the conquistadors were panning. They are the same atoms now that they were then. Time has done nothing to them. Now, set against that continuity, the chain of events that followed the moment that soldier threw his gray stone into the water. Other soldiers made the same mistake in the same rivers for another century and a half. Then the metal arrived in Europe in the hands of curious naturalists, and the story changed. Scientists spent a century trying to understand it. William Wollaston refined it and kept the secret that could have destroyed the British economy. It became the material of precision instruments, of laboratory crucibles that could withstand acids that destroyed everything else, of weights and measures, and the kilogram standard that anchored global commerce. It slipped into the nitrogen reactors and began quietly holding half of human civilization's food supply in its catalytic grip. It went into the exhaust systems of 1 billion cars and made city air breathable. Barnett Rosenberg ran electricity through platinum electrodes one afternoon in 1965 and changed the trajectory of cancer treatment for hundreds of millions of people. It defined, for 130 years, what a kilogram was. It is right now in the form of a spacecraft called Psyche, arcing through the darkness toward an asteroid. Every single link in that chain traces back to the moment a soldier threw a gray rock into a river and walked away. Not because he did something right, because he did something wrong. Because human beings, for most of history, have encountered things they do not understand and responded by discarding them. And platinum, with the patience of something that has already survived the death of the stars that made it, simply waited to be understood. There is a concept in philosophy, Kant's Ding an sich, the thing in itself, which describes the idea that objects have an existence independent of any observer's perception or use of them. A chair is a chair because we sit in it, but the wood and metal that constitute the chair exist regardless of what we do with them, in a way that is fundamentally indifferent to us. Platinum is perhaps the most pure example of a Ding an sich that human civilization has encountered. It does not need to be a ring to be platinum. It does not need to be a catalyst or a medical treatment or a kilogram standard. It is not improved by our applications or diminished by our ignorance. When the conquistadors called it garbage, it was not thereby made garbage. When we call it precious, it is not thereby made more precious. It is what it is, entirely and without apology, in complete indifference to our categories and our valuations and our history with it. And yet we are the ones who looked at the gray stone and eventually, after a century and a half of throwing it in rivers, stopped. We are the ones who asked, what is this, really? We are the ones who built the laboratories and the instruments and the theories and the intuitions that allowed us to answer that question, to follow the answer from the Columbian riverbed to the neutron star collision, to the late heavy bombardment, to the narrow reef 2 kilometers underground in South Africa, to the hospital ward where a patient is receiving a platinum compound through an intravenous drip. We are the ones who did that, not platinum. Platinum contributed nothing to this process except itself. It did not cooperate or resist. It did not reveal itself or hide itself. It simply existed, with complete equanimity, in whatever context it found itself, doing what its atomic structure made it do, resisting corrosion, catalyzing reactions, holding its form through time. The curiosity was ours. The persistence was ours. The ability to look at a gray stone and ask what it might mean, not just for this afternoon's panning session, but for the nature of matter and the origin of the universe and the chemistry of life, that is ours alone. We are mortal. We know we are mortal, which makes us unusual among the organisms that inhabit this planet. And we respond to that knowledge in 100 ways, with art, with religion, with science, with the particular urgency that comes from knowing that the time available to understand things is not unlimited. Platinum is not mortal. It does not know this about itself because it does not know anything. It does not experience the passage of the time through which it passes unchanged. It does not appreciate its own stability or take satisfaction in its own indifference to entropy. It is simply matter, arranged in a particular configuration, doing what that configuration compels it to do. We are matter too, arranged in a considerably more complicated configuration, doing what that configuration compels us to do, which includes, apparently, an irresistible compulsion to understand the other arrangements of matter that we encounter. And out of that compulsion, out of that restless, mortal, carbon-based curiosity, we have assembled the story you have just heard. A story that begins with garbage in a river and ends with spacecraft crossing the solar system. A story that contains, somewhere in the middle, the feeding of billions of people, the cleaning of city air, and the reprieve from cancer of millions of patients who did not know that the metal carrying their treatment had been forged in the collision of neutron stars. Platinum did not make that story. We did. Out of the irreducible human need to know what things are, and what they are for, and where they came from, and what they might yet do. Platinum provided the material. We provided the meaning. And in that exchange, between the eternal indifference of matter and the brief, urgent, extraordinarily productive curiosity of the beings who learn to read it, there is something that I think deserves the word that science is usually reluctant to use. There is something that deserves the word wonder. The soldier threw his stone into the river. The stone is still there, and we are still learning what it means. That is the story of platinum. And it is, in its own quiet way, one of the most astonishing stories that has ever been true.